On a cold laboratory bench that does not yet exist, in a calculation that has never once been tested, gravity does something it is absolutely forbidden to do. It pushes. Everywhere else in the universe, in the apple that falls, the moon that holds its orbit, the slow gathering of 100 billion stars into a single galaxy, gravity has only ever had one job, and it has never failed at it. It pulls things together. It never drives them apart. But early this year, 3 physicists found a loophole hidden inside the mathematics, a door in the one rule that never breaks, and what waits on the other side of that door is not a hovering car and not a floating city. It is a question about the true nature of the force that holds your entire world together. Is the most familiar thing in your life really as simple as it has always seemed? Get comfortable and let the noise of the day settle out of you. Subscribe if you have not, so you can keep drifting through the cosmos with us on quiet nights like this. And stay with me, because the door these 3 physicists found in the most ordinary force you know leads somewhere almost no one expects, all the way down to the beginning of the universe. Let's get into it. Part 1. The one rule that never breaks. There is one rule your body learned before you had words for anything, and it has never once let you down. Whatever you hold, if you open your hand, falls. The cup slides off the edge of the table and drops to the floor. The keys leave your fingers and go straight down. Rain does not hang in the air, and the coffee does not climb out of the mug. And in all the years you have been alive, in every room you have ever stood in, not one object has ever quietly drifted upward on its own. You do not think of this as physics. You think of it as the way the world simply is. Down is down. Things fall. It is the most dependable fact you own. That dependability goes far past the kitchen floor. The same pull that drops the cup is the pull that holds the oceans against the turning earth, that keeps the air from leaking off into space, that swings the moon around us month after month without ever letting it go. It reaches out from the sun and holds 8 planets on their long, patient loops. It gathers 100 billion stars into the slow wheel of a galaxy and keeps that wheel from flying apart. Everywhere we have ever looked, from a falling raindrop to the largest structures in the sky, gravity does the same single thing. It draws things together. It pulls. And here is the part that matters tonight. The part that is easy to miss precisely because it is so constant. Gravity only pulls. There is no version of it that pushes. There is no button to flip, no second setting, no anti-gravity hiding in the ordinary world. 2 lumps of matter are drawn toward each other, always and never, ever driven apart. Think for a moment about how strange that actually is, once you notice it. Almost every other force in nature comes with 2 faces. Rub a balloon on your hair, and you can make it stick to a wall or leap away from another balloon, because electric charge can attract or repel depending on its sign. Bring 2 magnets together the right way and they snap into place. Turn one around and they shove each other apart with a force you can feel in your wrists. Push and pull, north and south, plus and minus. That is the normal shape of a force. Gravity is the one exception, the lonely rule breaker that refuses to break. It has only one face. It says come here, and it never says go away. There is another strange thing hiding underneath the first one, and it deepens the puzzle rather than solving it. Gravity is not only the one force that refuses to push, it is also, by an enormous margin, the weakest force there is. That sounds impossible because gravity is the one you feel most, the one that aches in your legs at the end of a long day. But hold a small magnet over a paperclip and let it lift the clip off the table, and you have just watched a magnet the size of a coin win a tug-of-war against the gravity of the entire planet. The whole Earth, all 6,000 billion tons of it, pulling the clip down, and one little magnet pulling it up, and the magnet wins without effort. Gravity is so faint that it takes something the size of a world before you notice it at all, and yet this faint, one-way, almost embarrassingly weak force is the one that ends up shaping everything on the larger scales, gathering the stars, building the galaxies, deciding the fate of the whole universe. The weakest player at the table runs the game. Nobody fully knows why, and that quiet not knowing is the first loose thread we're going to pull. We are so used to all of this that we have built our whole sense of the world on top of it, without ever noticing the foundation was there. When you feel your own weight in your feet right now, that is gravity pulling every atom of you toward the center of a planet you cannot see the far side of. When you lie down tonight and feel the mattress take your weight, that is the same pull, the same one-way pull that has been holding you to the ground since the day you were born and will still be holding you on the last day of your life. It is the most intimate force there is. It is touching you constantly, everywhere, and it has never once done anything but hold you down. So imagine how it felt, early in the year 2026, when 3 physicists quietly posted a paper to a public archive of scientific research with a title that read like a small, calm impossibility. The title said, in plain language, that a repulsive gravitational force could be used as a witness of the quantum nature of gravity. Read past the technical words for a second and sit with the first 2 of them. Repulsive, gravitational, a gravitational push. The 3 names on that paper were Pablo Saldanha, a physicist working in Brazil, and Chiara Marletto and Vlatko Vedral, both at the University of Oxford. They were not cranks. They were not selling anything. They were serious researchers, and what they had done, on paper, with careful mathematics, was find a crack in the one rule that never breaks. Under the right conditions, they showed, gravity does not have to pull. It can be made to push. I want to be honest with you right at the start of tonight, because this is a story where the honesty is the best part, not a thing we have to get out of the way first. Nobody has built an anti-gravity machine. Nobody floated a coffee cup or a car or themselves. What these 3 physicists produced is a calculation, a proposal, a piece of theory that has not yet even finished the long process of being checked by other scientists. When one well-known physicist reviewed the paper for a general audience, she gave it a low score as a practical experiment while praising it warmly as an idea, because actually seeing this effect in a real laboratory would be extraordinarily hard and might be impossible for a very long time. So if you came here expecting me to tell you that we can now switch off gravity, I am going to disappoint you, and I am going to do it early. That is not what happened. What happened is stranger, and quieter, and in a way much larger. Because the real shock in this paper is not the push itself. The push is almost a side effect. The 3 physicists were not trying to invent anti-gravity at all. They were chasing a much older and much deeper question, one that has haunted physics for 100 years, and the gravitational push simply fell out of the mathematics while they were chasing it, like a coin you did not know was in your pocket falling out when you reach for your keys. And it turned out that this small, strange push, if we could ever see it, would be the clearest possible answer to the biggest unanswered question about gravity that exists. That is the thread we're going to follow tonight, slowly, all the way down. Here is the shape of what is coming, so you know the ground we will walk. First we have to understand the rule itself, really understand it, not just accept it. We have to see why gravity only pulls, why that one-way street is written so deeply into the best description of reality we have ever produced that it looks less like a law and more like the meaning of the word down. Then we have to meet the 100-year-old problem the 3 physicists were actually working on, the quiet war between our 2 greatest theories that no one has ever been able to end. Then, and only then, will the trick in this paper make sense, and you will be able to see for yourself how a single speck of matter, placed into 2 places at once, can reach out and shove another particle away, and why that shove would tell us something about the universe that we have wanted to know since before your grandparents were born. I am not going to rush any of it. This is not a story that works if you sprint through it. It is a story that works the way your eyes adjust to a dark room, where at first you see almost nothing, and then, slowly, without any single moment you could point to, the shapes come out of the black, and you realize the room was full the whole time. That is how understanding gravity feels once you actually look at it. You have lived inside this force every second of your life, and the truth is that we, all of us, the whole species, do not really know what it is. We can predict exactly what it will do. We can send a probe across billions of miles of space and have it arrive within seconds of the time we calculated, because our equations for gravity's pull are that good. And yet if you ask a physicist the simple question a child would ask, the question of what gravity actually is and whether it obeys the same underlying rules as everything else in the universe, the honest answer is that we are not sure. The thing closest to you, the thing touching you right now, is a stranger. That is the quiet fear underneath this whole story, and it is not the fear the title might make you expect. It is not the fear of falling, or of floating, or of some machine gone wrong. It is the fear you feel when you learn that something you trusted completely, something you leaned your whole weight against without a second thought, turns out to have a door in it you never knew was there. A door that has been there all along. A door that, when 3 physicists finally found the handle, opened not onto a floating car but onto a question about what holds the entire universe, and you along with it, together. So tonight, hold one question in your mind and try not to answer it too soon, because the whole video is really an attempt to earn the answer honestly. The question is this: if the one force that only ever pulls can, under the right conditions, be made to push, then how well did we ever really understand the thing that has been holding us down our entire lives? Keep that with you. We are going to follow it all the way to the beginning of the universe and back, and by the end I think the word terrifying will have turned into something else entirely in your hands. Let us start where everything starts. Let us start by looking, really looking, at why things fall. Part 2. The Valley That Only Goes Down. To understand why a gravitational push is such a shock, we have to understand why the pull is so total, and for that we have to go back a little more than 300 years, to a man sitting in the English countryside during a plague year, watching things fall. Isaac Newton did not discover that objects drop. Everyone already knew that. What Newton did was far bolder. He looked at an apple falling from a tree, and then looked up at the moon hanging in the sky, and he had the almost reckless idea that these were the same thing. The apple falls because the earth pulls it. The moon, he realized, is also falling toward the earth, constantly, forever. But it is moving sideways so fast that it keeps missing, curving around us instead of crashing down. One pull, he proposed, reaches from the earth to the apple and to the moon and beyond, and in fact stretches between every pair of objects in the universe. Every mass pulls every other mass. He wrote this down in the 1680s, and it was so accurate that we used it, unchanged, to fly human beings to that same moon 3 centuries later. But look closely at Newton's law, because there is a silence inside it that becomes the whole story. In Newton's picture, there is only attraction. Mass draws mass. There is no term for pushing, no antimass, no negative version of gravity you could set against the ordinary kind. Electricity has positive and negative charges, and they can attract or repel. Gravity, in Newton's mathematics, has only one kind of source, and it only ever draws inward. He never explained why. He described the pull with a precision that still holds up today, and he was famously honest that he had no idea what gravity actually was, or how it reached invisibly across empty space to tug on the moon. He gave us the how and left the what completely open. That gap sat there, unfilled, for more than 200 years. Then, in the early years of the 20th century, a patent clerk turned physicist filled it, and his answer is the reason the word repulsive feels so impossible next to the word gravity. Albert Einstein, in 1915, proposed that gravity is not a force reaching across space at all. Gravity, he said, is the shape of space and time themselves. Mass and energy bend the space around them, and everything else, moving as straight as it can through that bent space, simply follows the curve. Nothing is being pulled by an invisible rope. Things fall because the ground they are moving through is warped, and they are rolling downhill in a landscape you cannot see with your eyes but can feel in your bones. The picture almost everyone has heard is the heavy ball on a stretched rubber sheet, and it is worth slowing down on because it hides the exact thing we need. Imagine a taut sheet of rubber, pulled flat, and you set a heavy ball in the middle. The sheet sags, forming a dip, a valley with the ball at the bottom. Now roll a small marble across the sheet nearby, and instead of going straight, it curves toward the dip and spirals in. That curving is gravity. The Earth is not tugging the moon with a rope. The Earth is the heavy ball, and it has carved a valley in the shape of space, and the moon is the marble rolling around the rim of that valley, never quite falling in. You are a marble too right now, resting at the bottom of the valley the Earth has dug, held against the floor not by a rope, but by the shape of the space you're sitting in. Here is the part that changes everything, the part hidden inside the rubber sheet. A heavy ball always makes a dip that goes down. It sags the sheet downward, and so every marble nearby rolls inward toward the mass. To make gravity push, you would need the opposite. You would need something that lifts the rubber sheet into a hill instead of a valley, so that marbles roll away from it rather than toward it. And in Einstein's mathematics, the thing that bends space is mass and energy. And mass and energy, as far as anyone has ever measured, in every experiment ever done, are always positive. There is no negative mass to raise the sheet into a hill. Every source of gravity we know of sags the sheet the same way, downward, and so gravity, in the deepest and most tested description we have, can only ever pull things in. The one-way street is not an accident of the kitchen floor. It is written into the geometry of reality. I want you to sit inside that for a moment, because it is the wall this whole story is about to run into. Imagine you are the marble. You have rolled across this sheet your entire existence, and every direction that has ever mattered has curved the same way. Toward, downhill, inward. You have never seen a slope that rises. You do not even have a word for up, not really, because nothing in all your rolling has ever lifted you. Every valley you have ever found had a bottom, and you always ended up at it. The idea of a hill, a place where the ground pushes you away, is not just unfamiliar to you. It is against everything the sheet has ever taught. Falling is not something that happens to you. Falling is simply what existing on the sheet means, and then, far out at the edge of the sheet, at the very limit of where you can see, you notice something you have no name for. A place where the rubber seems, just barely, to curl the wrong way. A hint of a slope that rises instead of falls. You cannot quite reach it. You cannot even be sure it is real. But it is there, at the edge of everything you know, a suggestion that the one rule you are certain of might somewhere bend backward. And you cannot look away from it. It helps to know just how well tested that valley is, because it explains why physicists guard the rule so fiercely. Einstein's picture of gravity as curved space is not a pretty story we tell for lack of anything better. It is arguably the most successful idea in the history of science. It predicted that the planet Mercury would drift around its orbit by a tiny amount that Newton's version got wrong, and it was right, down to the second of arc. It predicted that starlight passing the edge of the sun would bend, and in 1919 astronomers watched it happen during an eclipse. It predicts that time itself runs slightly slower far down in a gravitational valley, which sounds like poetry until you learn that the satellites overhead have to correct for it constantly, because without that correction the maps on your phone would drift wrong by miles in a single day. 100 years of the hardest test we could throw at it, and Einstein has never once been caught in a mistake. So when this theory tells us gravity only pulls, that is not a casual guess we would happily throw away. It is a conclusion carrying the full weight of the most reliable description of reality we have ever built. To get a push, you cannot just wish the rule away, you have to find a crack it never knew it had. That edge is where the three physicists have been standing. Everything about the ordinary world, everything Newton and Einstein taught us, says that edge should not exist, that the sheet only ever sags, that mass only ever pulls. For attraction to become repulsion, you would need to reach outside the classical picture entirely, outside the smooth, certain geometry of Einstein's curved space, into somewhere the rules are different. And there is exactly one place in all of physics where the rules are different. There is one part of nature that does not play by the smooth, definite mathematics of the rubber sheet. Hold on to that phrase, outside the classical picture, because that is precisely the door the new paper walks through, and it has a name you already know, even if you have never connected it to gravity before. There is one more piece to lay down before we get there, and it comes from the strange language physicists use to describe forces. In modern physics, every force is carried by a kind of messenger, a particle that passes between objects and communicates the push or the pull. Light and electricity are carried by a messenger called the photon, and because of the particular properties of that messenger, electric charges can both attract and repel, which is why magnets have two ends. Gravity, in the theories that try to make it a quantum force, would be carried by a different messenger, one that has never been directly detected, sometimes called the graviton. And the mathematics says that because of the specific nature of that gravitational messenger, its particular kind of spin, every source of gravity must attract every other source, like draws like. There is no configuration that repels, so from every direction we approach it, from Newton's apple to Einstein's curved space to the quantum language of messengers, we arrive at the same stubborn conclusion. Gravity pulls, only pulls, always pulls. Which is what makes the next part of the story feel, at first, like a magic trick, or a mistake, or a violation of something sacred. Because the three physicists did not find negative mass. They did not invent a new messenger. They did not overturn Einstein. they did something far sneakier and far more interesting. They found a way to keep every one of these rules intact, to use ordinary attracting positive mass, and still, out the other end, get a push. And to see how, we have to leave the smooth, certain world of the rubber sheet behind and step into the one part of nature where an object does not have to be in a single, definite place at all. We have to talk about the other great theory of the 20th century, the one that describes the very small and about the 100-year war it has been quietly fighting with gravity this entire time, a war that neither side has ever won. Part 3. 2 manuals for the same universe. The crack the 3 physicists found does not live in gravity. It lives in the collision between gravity and the other great discovery of the 20th century, and to feel that collision, you have to meet the second theory on its own terms. While Einstein was describing the very large, the smooth curve of space around stars and planets, a different group of physicists was descending into the very small, into the world of atoms and the particles inside them, and what they found there did not look like the smooth, certain world of the rubber sheet at all. It looked, frankly, insane, and it has passed every test we have ever devised, which means the insanity is real. In the world of the very small, the world quantum mechanics describes, a particle does not have to be in one place. It can be in a blur of many places at once, a state physicists call superposition, spread out like a wave until the moment something measures it and forces it to pick a single spot. An electron does not travel from here to there along one path like a thrown stone. It travels along all the paths at once, and the paths add together and interfere, the way ripples on a pond can reinforce into a tall peak or cancel into flat water. Nothing in this world has a single definite value until it is looked at. Everything comes as a spread of possibilities, as probabilities, as maybe. It is the opposite of the rubber sheet in almost every way. The rubber sheet is smooth, continuous and certain. The quantum world is grainy, made of discrete little packets, and it is uncertain all the way down to its foundations. Here is the thing that should stop you. Both of these theories are correct. Not correct for now, not correct until something better. In their own domains, both general relativity and quantum mechanics have passed every single experimental test ever thrown at them for about 100 years without one confirmed failure between them. Quantum mechanics predicts certain properties of the electron and matches the measurement to better than 1 part in a trillion, which is like predicting the distance from New York to Los Angeles and being right to within the width of a human hair. General relativity, as we said, has never missed either. We have, in our hands, 2 flawless descriptions of reality, and they contradict each other. They contradict each other because they are built on foundations that do not fit together. One describes a smooth, continuous, definite space-time. The other describes a grainy, probabilistic world of things that can be in many states at once. Every other force in nature, electricity and magnetism, and the 2 forces inside the atomic nucleus, we have successfully rewritten in the quantum language. We taught them to speak probability, and they spoke it fluently. But when we try to do the same to gravity, when we try to make Einstein's smooth curved space into a quantum thing that can be in a superposition of shapes, the mathematics detonates. The equations start producing infinities, answers of infinite size that mean nothing, and unlike in the other forces, there is no known way to tame them. Gravity, alone among the forces, refuses to be made quantum. It will not fit in the box. It is worth being precise about where the 2 manuals clash, because it is not everywhere. In almost every situation you can imagine, 1 manual is enough. When you are dealing with something large, like a planet or a falling apple, gravity matters and the quantum blur is far too small to notice, so you use Einstein and you are fine. When you are dealing with something tiny, like an electron, the quantum rules matter, and gravity is so absurdly weak you can ignore it completely, so you use quantum mechanics, and you are fine. The 2 manuals almost never have to be open at the same time, which is exactly why we got away with the contradiction for 100 years. The trouble only appears in the rare places where something is both very heavy and very small at once, where you would need both manuals open together and they refuse to agree. There are only a couple of places in all of nature like that. One is the center of a black hole, where a huge amount of matter is crushed into a point. The other is the very first instant of the universe, where everything that exists now was packed into something smaller than an atom. In other words, the 2 places where the manuals contradict each other are the beginning of everything and the inside of the darkest objects in the sky, the exact two places we most want to understand and cannot. One physicist described this situation, for a general audience, with a joke that is worth carrying with you for the rest of the night, because it is more honest than most textbooks. It is, she said, like having two instruction manuals for the universe. One manual says, assemble with screws. The other manual says, there are no screws. And then a theorist walks in and cheerfully suggests, well, have you tried 11 dimensions? Two instruction manuals for the same universe, and they do not agree on the most basic parts. That image is going to come back later tonight, so hold on to it. Two manuals, one reality. And a seam running down the middle that no one in 100 years of trying has ever managed to cross. I want you to sit with the strangeness of that, because it is easy to hear and hard to actually feel. We tell ourselves, as a species, that we understand the universe. We put it in school books. We speak about the laws of physics as though they were a single, finished, agreed-upon thing. But that is not true, and the people who know the most are the ones most willing to admit it. We do not have one description of reality. We have two brilliant half maps, each perfect in its own territory, and where the two territories meet, at the places where something is both very heavy and very small, at the center of a black hole, at the first instant of the universe, the two maps disagree completely, and we simply do not know which way to walk. You, sitting here right now, are one of those places where the two territories meet. Your body is held together, atom by quantum rules, the grainy probabilistic ones, and your whole body is held down, this very second, by gravity, the smooth curved space one. Both manuals are being used to build you at the same moment, and read side by side, the two manuals do not agree about what kind of thing you are. That is not a frightening fact exactly. It is a humbling one, and there is a difference. The two smartest ideas humanity has ever produced, the two that between them account for literally everything anyone has ever measured, from the falling apple to the shining star to the current running through the device in your hand, cannot both be the final truth. One of them, or both, is a beautiful approximation of something deeper that we have not found yet. 100 years of the most gifted minds who have ever lived have tried to make them agree, and the seam is still there, uncrossed. When you look up at the night sky and feel that it is all understood, that somewhere in a book the whole thing is written down, remember the two manuals. We are not standing on a finished map. We are standing at the edge of one, holding a second one that does not match, squinting at the gap between them, and in that gap sits the specific question the three physicists were actually trying to answer, the question that quietly matters more than almost any other in physics. It is not, at first, a dramatic question. It sounds almost technical. But everything tonight turns on it. The question is simply this: is gravity quantum at all? We assume it must be, because every other force is, because it would be strange for gravity to be the one classical exception in a quantum universe. But we have never checked. We have never once caught gravity behaving in a quantum way, never seen it spread into a superposition, never watched it do anything but sag the smooth rubber sheet the way Einstein described. It is entirely possible that gravity really is different, that it really is classical, that the rubber sheet is the whole truth, and the quantum world simply rides on top of it. We do not know. After 100 years, the most basic question about the nature of gravity, whether it obeys the same underlying rules as everything else, is still open. The trouble was always that testing it seemed impossible. To see gravity behave quantumly, you would need something both heavy enough to have noticeable gravity and small enough to go into a quantum superposition, and those two demands seem to point in opposite directions. For most of the last century, physicists assumed the only place the question could ever be answered was somewhere no human could ever go, in conditions no laboratory could ever reach. The dream was to somehow catch gravity in a genuinely quantum act, to see it do something a smooth classical field simply cannot do, and thereby settle the question once and for all. But that seemed to belong to a future century, or to no century at all. And then, quietly, over the last decade or so, a few physicists began to wonder whether they had been wrong about that. They began to ask whether the impossible test might, just possibly, be done not at the birth of the cosmos, not inside a black hole, but on a table, in a room, with equipment you could in principle build. It was a wild thought, and the paper we are here to talk about tonight is one of its strangest and most beautiful children. Part 4. Catching Gravity in the Act. To understand the trick in the new paper, you first have to understand the idea it grew out of, because for about the last 10 years there has been a quiet revolution in how physicists think about testing gravity, and almost no one outside the field has noticed it happening. For most of the 20th century, the assumption was simple and discouraging. If you want to see gravity behave in a quantum way, you need enormous energies, the kind that only exist inside a collapsing star or in the first sliver of a second after the birth of the universe. Those are not places you can build an experiment. So the question of whether gravity is quantum was treated almost as a philosophical one, interesting to argue about over coffee, impossible to ever actually answer. It was filed under someday or under never. Then a handful of physicists looked at the problem from a completely different angle, and their idea was so clever that when you first hear it, it sounds like cheating. Instead of trying to reach the violent energies where gravity and the quantum world both scream, they asked a gentler question. What is the one thing that only a quantum object can do, the fingerprint that no ordinary classical thing could ever fake? And the answer they landed on is a phenomenon called entanglement. Entanglement is one of the strangest features of the quantum world, a kind of connection between two particles so intimate that measuring one instantly tells you about the other, no matter how far apart they are. Einstein himself hated it and called it spooky. But it is real. It has been tested thousands of times, and here is the crucial part. Entanglement can only be created by a quantum process. A purely classical influence, something that obeys the smooth, definite rules of the rubber sheet, can never entangle two things. It is simply not powerful enough. Entanglement is a signature that quantum mechanics, and only quantum mechanics, has been at work. Now watch how they turn that into a test of gravity. Suppose you take two small objects, each heavy enough that its gravity is not completely negligible, and you place each of them into a quantum superposition so that each one is, in the quantum sense, in two positions at once. Then you let them sit near each other, and you make sure that the only thing connecting them, the only force that can pass between them, is gravity. You shield out everything else, and then, after a while, you check whether the two objects have become entangled. Here is the whole argument in one sentence. If they come out entangled, and gravity was the only thing that could have connected them, then gravity itself must have carried the entanglement, which means gravity itself must be quantum. Because remember, only a quantum process can entangle. If a classical rubber sheet gravity had been passing between them, it could never have produced that spooky connection. So the entanglement would be a witness, a piece of direct evidence, that the gravitational field had been doing something only a quantum thing can do. If that logic went by too fast, let me slow it down with a picture, because it really is the hinge of the whole field. Think of entanglement as a secret that two particles can only share if something quantum whispered it to both of them. There are only certain kinds of messengers that can carry that particular secret. A classical messenger, no matter how it tries, physically cannot deliver it. So imagine you seal two particles in separate boxes, and you allow exactly one thing to pass between those boxes, and that one thing is gravity. Nothing else. No light, no electricity, no touch, only the faint gravitational tug of one mass on the other. You wait. Then you open the boxes and check whether the two particles are now sharing the secret, whether they have become entangled. If they have, there is only one possible culprit because gravity was the only messenger you let through. And since a classical messenger can never carry that secret, the gravity that passed between them cannot have been classical. It must have been quantum. You would have caught gravity, at last, doing the one thing only a quantum field can do without ever going near a black hole. That is the beauty of the idea, and it is why it electrified the field. This idea was worked out around the year 2017 by several physicists, including a group led by Sugato Bose, and, independently, by two of the same names on the paper we are discussing tonight, Chiara Marletto and Vlatko Vedrol. And it changed everything about how the field thought. Suddenly, testing whether gravity is quantum was not a fantasy requiring the energies of a black hole. It was in principle a tabletop experiment. Hard, yes, absurdly hard. But no longer impossible in principle. You would not need a collapsing star. You would need two tiny masses, exquisite control, and a way to keep the quantum blur alive long enough to matter. The question had come down out of the heavens and onto a laboratory bench, and that shift is the soil the new paper grows in. But I said the experiment is absurdly hard, and I need to explain why, because the difficulty is not a small detail. It is a dragon, and it guards every door in this entire field. The problem is that the quantum blur, the superposition, the being in two places at once, is astonishingly fragile for anything larger than a single particle. The bigger and heavier an object is, the faster its quantumness leaks away into its surroundings, a process physicists call decoherence. A lone electron can hold a superposition almost forever. A large molecule can manage it for a fraction of a second. A dust grain, for all practical purposes, cannot manage it at all. The moment it interacts with the light and air and warmth around it, its quantum spread collapses into a single ordinary position, far too fast to ever catch. This is not a technical inconvenience. This is the reason the whole world around you looks solid and definite and singular. It is the reason you have never seen a friend be in two places at once, never watched a coffee cup blur into a superposition of the table and the floor. The quantumness is there in principle for everything, but for anything big enough to see, it drains away so fast that the world snaps into a single, classical, definite picture before you could ever notice the blur. Which means the whole game, in these experiments, is a fight against decoherence. You're trying to take something heavy enough to have measurable gravity and hold it in a quantum superposition long enough to do the test, before the dragon of decoherence wakes up and destroys the very thing you're trying to measure. And heavier means the dragon wakes faster. It is a brutal trade. The heavier you go to get more gravity, the more violently the quantum blur wants to collapse. This is the wall every experiment in this field slams into, and it is the wall the new paper is trying, with great cleverness, to lower. It helps to know just how far we have already come against that dragon, because the progress is genuinely wonderful, and it is the reason anyone dares to dream this is possible at all. Back in 1999, physicists managed to put a molecule of 60 carbon atoms, a tiny soccer ball of carbon called a buckyball, into a superposition, sending it through an experiment where it interfered with itself, going through two paths at once, exactly like the electron. That was already remarkable, a molecule you could almost think of as an object, behaving like a quantum wave, and they did not stop there. By the year 2019, other physicists had pushed this up to molecules made of more than 2,000 atoms, objects thousands of times heavier than that first buckyball, and still, when handled with enough care and kept cold and isolated enough, they blurred into superpositions and interfered with themselves. There is no known hard wall, no size at which the quantum rules simply switch off. It just gets harder and harder and harder the bigger you go. The dragon gets stronger, but it has not yet won. There is something quietly moving about that fight, if you let yourself feel it. Every time you've ever reached out and touched something solid, every time you've set your hand flat on a table and felt it hold, you are feeling the victory of decoherence. The table is definite and single and there, not blurred across two places, precisely because it is large and warm and constantly interacting with the world, and all of that interaction crushes its quantum spread into one solid fact, billions upon billions of times a second. The ordinary, reliable, touchable world is not the absence of the quantum strangeness. It is the quantum strangeness, drowned out, averaged away, hidden under the sheer weight of everything touching everything else. These physicists are trying to build a tiny, cold, shielded pocket, where that drowning is held off for a heartbeat, where something almost large enough to see is allowed to stay quantum just long enough to ask it a question about gravity. They are trying to hold open, by hand, the door the whole universe is constantly slamming shut. So this is where the field stood when the three physicists sat down to work. The dream was alive but distant. The entanglement witness idea gave a real path to answering the 100-year question, but it needed two heavy objects, each in a superposition, held in place against the dragon of decoherence long enough to entangle through gravity alone. Two superpositions is doubly hard, twice the fight, twice the fragility, and it was here that the paper made its move, the move that led, almost by accident, to a gravitational push. Because Saldanha, Marletto and Vedral found a way to do it with only one. Part 5. One speck, two places. The move the three physicists made was to stop trying to put two heavy objects into superposition and settle for one. Their setup uses a single source mass and a single probe. The source is the object you place into a quantum superposition, coaxing it into being in two positions at once, which we can simply call the first place and the second place. The probe is a second, much lighter particle that you set nearby, and your whole job is to watch, very carefully, how the probe responds to the gravity of the source. That is the entire experiment in its bones. One mass in two places, one light particle beside it, and a question about which way the light particle drifts. Let us walk through what ordinary intuition predicts, because the whole shock of the result is the gap between what you expect and what the mathematics says. If the source was simply, definitely sitting in the first place, then its gravity would pull the probe gently toward the first place. That is just Newton and Einstein, the pull toward mass. And if the source was simply, definitely in the second place, then its gravity would pull the probe gently toward the second place. No surprises yet, both are ordinary attraction. So now, common sense says, if the source is somehow spread between the two places, the probe should just feel a pull toward the middle, toward the average of the two positions, splitting the difference. A little tug this way from the first place, a little tug that way from the second place, and the two average out to a gentle pull toward the point between them. Attraction still. Always attraction. Toward the middle. That is what anyone would guess, and it is what a classical rubber sheet gravity would deliver. If the source were just a tiny ball at some fuzzy, uncertain location, the probe would be drawn toward its average spot, and that would be the end of it. But the source is not a tiny ball at an uncertain location, and this distinction is the beating heart of the entire story, so I want to be careful with it. There is a difference between not knowing where something is and something being genuinely in two places at once, and it is one of the most important differences in all of physics. If I flip a coin and cover it with my hand, the coin is definitely either heads or tails, I just do not know which. That is ignorance. The coin has a single real state, and I am merely uncertain about it. A quantum superposition is not that. When the source mass is placed into a superposition of the first place and the second place, it is not secretly in one of them while I remain in the dark. It is, in the fullest physical sense the theory allows, in both. Both positions are real at once. And an object in two places at once is not really a ball at all anymore. It is a wave spread across both locations, and that changes what its gravity does, because waves do something balls cannot. Waves interfere. We know this is not mere ignorance because of experiments we have already talked about, the ones where a single molecule goes through two slits at once, and then interferes with itself on the far side. If the molecule had secretly gone through only one slit, and we were simply ignorant of which, there would be no interference pattern, no bands of arrival and absence. You would just get two ordinary piles. The interference pattern only appears because the molecule genuinely took both paths, and the two versions of it met on the other side and added and cancelled like waves. That pattern is the fingerprint of a real superposition, and we have seen it, over and over, in the laboratory. So when the physicists say the source mass is in two places at once, they do not mean it in a loose or poetic way. They mean it in the same hard, tested sense that makes the interference bands appear. The source is not a ball with an unknown address. It is a wave with two crests, and its gravity, whatever gravity turns out to be, has to somehow come from both crests at the same time. That is the strangeness the probe is about to report on. Two sources of pull, from one object, that is really one object being two things at once. I want to put you in the room for this, because it is the moment everything turns, and it deserves to be felt and not just understood. Picture a laboratory bench, cold and very still. The air has been pumped away. The lights are low. On the bench, held in a trap of fields you cannot see, is a single speck of matter, so small it would be invisible to your eye, and that speck has been coaxed, with enormous care, into a state where it is in two places at once. Not blurred, not uncertain, not maybe here, maybe there. Genuinely occupying two positions at the same time, a small standing wave of matter, present in both spots as fully as you are present in your chair. And a short distance away sits the probe, the lighter particle, waiting, feeling the gravity of the speck. Every instinct in your body, every year of watching things fall, every marble you have ever imagined rolling down a valley, is screaming the same prediction. The probe will drift toward the middle. It has to. Two pulls, one from each position of the speck, and they will average, and the probe will ease gently toward the point between them, the way anything caught between two magnets settles into the space between. You lean in to watch. You hold your breath. You already know what has to happen, because it is the only thing that has ever happened, in every room, in all of history. The probe will move toward the mass. It always moves toward the mass. That is what gravity is. And you keep watching, because in the quantum world, What has to happen and what does happen are not always the same thing. Stop for a moment and notice what is actually being attempted here, because it is easy to lose in the machinery. The wave nature that lets a particle be in two places at once is the single strangest fact about the small-scale world, the thing that makes the quantum world feel like a different country from the one your body lives in. Gravity is the most familiar force there is, the one that has been with you every second since birth, as ordinary as your own weight. And this experiment is an attempt to make those two things touch, to take the deepest strangeness of the very small and let it reach up and change what the most familiar force in the universe does. If it works, the smallness and the largeness, the grainy uncertain world and the smooth heavy one, the two manuals that have refused to agree for 100 years, would be caught in a single moment doing a single thing together. The whole reason the probe on that cold bench matters is that it sits exactly on the seam between the two maps, and it is being asked to say, with which way it drifts, whether that seam is real. Here is the physics underneath the held breath. Because the source is a wave spread across two positions, the probe does not feel one clean pull with one clean direction. It feels a combination of contributions, one associated with each position of the source, and those contributions are not just numbers to be added up like two people pulling on a rope. They are wave-like, and wave-like things interfere. Think of ripples on a pond. Drop two stones and the ripples spread out and cross, and where two crests meet they add into a taller crest, and where a crest meets a trough they cancel into flat, still water. The two contributions to the probe's motion behave the same way. In most situations they add up roughly the way you expect, and the probe is pulled inward, toward the source, ordinary attraction, nothing strange. But interference is a subtle thing, and it does not always add. Sometimes it cancels, and under the right, carefully arranged conditions, the two gravitational contributions from the two positions of the source can interfere in such a way that they do not add up to a pull toward the middle at all. They can add up to something no classical gravity could ever produce. I'm not going to tell you yet exactly what they add up to, because the whole meaning of this story lives in that result, and it deserves its own moment rather than being buried at the end of a paragraph about ponds. But I will tell you this much, to hold you until we get there. The reason this matters, the reason 3 serious physicists wrote a paper about it, and a careful skeptic still called it a genuine contribution, is that whatever the probe does in these special arranged runs, it does something that a smooth, definite, classical gravitational field is simply forbidden from making it do. The probe becomes a kind of reporter. Its motion carries a message about whether the gravity acting on it came from a definite source, or from a source that was truly, quantumly, in two places at once. And in that message, if we could ever read it clearly, is the answer to the 100-year-old question, is gravity quantum? The probe, drifting on its cold bench, would know something we have wanted to know for 100 years. So let us stop circling it and finally ask the plain question. In those special, carefully arranged runs, when the two crests of the wave interfere just so, which way does the probe actually move? Let us talk about the wrong way kick. Part 6. The wrong way kick. In those special runs, the probe moves the wrong way. It does not drift toward the middle. It does not ease gently toward the average of the two positions of the source. It is pushed away. The gravity of the speck, that single speck of ordinary positive matter, reaches out and shoves the probe in the opposite direction from everything you expected, everything Newton and Einstein and a lifetime of falling had promised, a wrong-way kick. Gravity, for that run, in that direction does not pull. It pushes. The one force that only ever draws things together drives them apart. The physicist who reviewed this paper for a general audience had exactly the reaction you are probably having, and she said it out loud because there is no dignified way to hide it. "Wait," she said. "What?" That is the honest response of a trained physicist reading this result for the first time. Not a calm nod, not a knowing smile. Wait. What? Because it looks, at first, like a violation of something sacred, like watching water flow uphill or a shadow fall in the wrong direction. Gravity is not supposed to be able to do this. It is the rule that never breaks. And here, on paper, in careful mathematics that has been checked and rechecked, is gravity breaking it. Now I need to hold you here, at the peak of the strangeness, and explain why this is not a trick, not a mistake, and not, as your instincts might be shouting, a violation of the laws of physics. Because the wrong way kick is real within the mathematics, and the reason it happens is the same reason it matters so much. Remember the ponds. The probe feels two contributions to its motion, one from each position of the source, and those contributions are wave-like, and waves interfere. In the ordinary runs, they add up more or less the way you expect, and you get attraction. But interference has another mode. When two waves meet crest to trough, they cancel, and if you arrange the geometry with enough care, the two gravitational contributions can be made to cancel their inward pulls and leave behind a net outward push. The probe is not being pulled toward one position and repelled from the other. It is feeling the combined, interfered result of a source that is genuinely in two places at once, and that combined result, in these special configurations, points outward. It points away. There is a slightly deeper way to see it that helps the strangeness settle. A particle that is spread out as a wave does not have one single, definite momentum, one clean speed and direction. It carries a whole spread of possible momenta at once, mixed together the way a musical chord is many notes sounding as one. When the source is in two places, the gravitational nudge it gives the probe is built from that whole spread, and the pieces of the spread can reinforce or cancel, just like the notes of a chord can swell or beat against each other. Line them up one way, and they swell into an inward pull. Line them up another way, the special way this experiment arranges, and they beat against each other until what is left over points outward. There is also a subtle piece about which runs you count. The physicists do not claim every single run shows a push. They prepare the source one way, measure it a particular chosen way at the end, and keep only the runs that come out matching that final measurement. In those selected runs, the interference lands so that the probe was pushed. It is a real effect, not a fudge, but it lives in a chosen slice of all the runs, not in a steady, always-on force. Hold that detail lightly for now. It will matter a great deal when we ask whether you could build a machine out of this. Here is why that single fact is worth a paper, worth 100 years of waiting, worth your attention on a quiet night. A classical gravitational field can never do this. I want to say that as plainly as I possibly can, because it is the whole point, and everything else tonight has been building toward it. In the smooth, definite, rubber-sheet world of Einstein, where a source mass sits at a single real location and dimples space into a single real valley, there is no arrangement, none, that produces a push between two ordinary positive masses. The valley only goes down. Attraction is the only thing on the menu, so if you were ever to see this wrong way kick in a real laboratory, and if you had done your job and ruled out every other force that might have faked it, then you would be looking at something that a classical gravitational field is strictly forbidden from producing. You would be looking at proof that the gravitational field itself had been in a superposition, that gravity in that instant had been behaving quantumly. The push would be the fingerprint, the push would be the witness. Let that reframe land, because it changes what this whole story is about. The push is not the point. I know the word antigravity makes you think the push is the prize, the goal, the treasure at the end. It is not. The push is almost incidental. It is a flag. It is the visible, unmistakable signal that says the thing that just acted on this probe was not classical, was not Einstein's smooth, certain valley, was something quantum. The three physicists did not set out to make gravity push. They set out to find a clear, unambiguous sign that gravity is quantum, and the wrong way kick is the cleanest sign they could imagine, because it is something a classical field simply cannot fake. Other tests, like the entanglement witness, ask you to detect a subtle, spooky correlation between two objects, which is delicate and hard to read. This test asks you to detect a push where there should only ever be a pull. If you see the push, and you have been careful, you are done. Gravity is quantum. The 100-year question is answered. The two manuals share at last a single sentence. It is worth pausing on why a classical field is so completely locked out of this, because it is the hinge the whole claim hangs from. Go back to the valley in the rubber sheet. In the classical picture, the source mass is at one real location, and it makes one real valley, and the probe rolls toward it. Even if you did not know exactly where the source was, even if it were jittering around, the classical field at any instant is still just some single definite valley, and a valley only ever pulls things down into it. There is no way to add up definite valleys and get a hill. You can average blurry valleys, you can shift them around, but every one of them slopes the same way, so their sum still slopes the same way, still pulls inward. The only path to a push is to let the source not have a single definite valley at all, to let it be a genuine superposition of two, so that what the probe feels is not the sum of two definite pulls, but the interference of two possibilities. An interference is a purely quantum thing, A classical field cannot interfere with itself because it is only ever in one state at a time, so the push, if it appears, could not have come from a classical field. There is no loophole in the loophole. That is why the wrong-way kick is such a clean witness. It is not merely unlikely for a classical field to produce, it is impossible. I want you to feel the size of what that would mean, standing at this peak before we climb back down into the honest difficulties. For your entire life, and for all of recorded history before it, gravity has done exactly one thing. It has pulled. Every apple, every tide, every held breath, every falling star. And here, in a calculation, is a way to make it, for one flickering run of one exquisite experiment, do the opposite, to run backward. Not because Einstein was wrong, not because there is secret negative mass, not because someone broke a law, but because the source of the gravity was allowed to be two things at once, and the two things interfered the way only quantum things can. The wrong-way kick is what it looks like when the smallness reaches up and touches the largeness. It is what it looks like when the two manuals for a single instant are open to the same page. There is a chill in this, and it is worth naming, because it is the honest version of the fear the title promised. The chill is not that a coffee cup might float. The chill is subtler and I think larger. It is the realization that the force you have leaned on your whole life, the force that has never once surprised you, the most predictable presence in your existence, has hidden inside it this whole time the capacity to do the one thing you were certain it could not. The wrong-way kick has always been possible. The mathematics was always there. We just did not know how to look for it. And that raises a question that will follow you out of this video and into the rest of your night. How many other things that you are certain about, how many other rules that have never once broken in your experience are hiding a door you have simply never found the handle to? Gravity kept its secret for 300 years after Newton, 100 years after Einstein. What else is keeping one? But before we let this become too large, I have to be honest with you again, because I promised at the start that the honesty would be the best part. You have just heard the most dramatic version of this story, the peak, the wait what, and your instincts are right to be suspicious of anything that sounds like gravity breaking its own law. So the very next thing we have to do is turn this result over and ask the hard questions. Does this not violate conservation of energy? Could you build a machine from it, a source of endless free push? Is this really a loophole, or is it a kind of accounting trick, a strange way of describing something that averages out to ordinary attraction in the end? Those questions have answers, good ones, honest ones, and the answers are the reason a careful skeptic could look at this same wrong-way kick and, without denying any of its beauty, quietly rate it 2 out of 10 as a practical experiment. So let us cool the room back down and ask whether the universe is really letting us cheat. Part 7. No free lunch. The first suspicion anyone sensible has, hearing that gravity can push, is that somebody must be getting something for nothing. If you can make gravity shove a particle away, then surely you can set up a clever arrangement that keeps shoving, over and over, and harvest that push as free energy. A perpetual motion machine dressed in quantum clothing. This is exactly the right worry to have, and the answer is a clean and firm no, and understanding why is what turns the wrong-way kick from a suspicious magic trick into an honest, if strange, piece of real physics. The key is something I asked you to hold lightly a few minutes ago, the fact that the push does not show up in every run. Remember how the experiment works. You prepare the source in a superposition, you let the probe respond, and then you make a particular measurement at the end, and keep only the runs that come out a certain way. In that selected slice of runs, the probe was pushed. But that is a slice, not the whole. If you step back and look at all the runs together, every single one, the pushed and the not pushed and everything in between, and you average them, you get exactly what ordinary physics demands. On average, the probe is attracted toward the average position of the source. The attraction is still there, underneath everything, whole and unbroken. The push lives only in a carefully chosen subset, and to get that subset you have to throw runs away. You do not get a steady, reliable force pointing outward that you could bolt a machine to. You get a strange statistical result that appears when you select certain outcomes and discard the rest. This is the difference between a genuinely strange result and a free lunch, and it is worth being precise about it. No conservation law is broken. Energy is not created. Momentum is not conjured from nothing. If you tried to build a perpetual motion machine out of the wrong-way kick, you would fail, because the moment you demand a push you can use every time, reliably, without throwing runs away, the effect vanishes and ordinary attraction returns. The universe, in its stubborn honesty, balances its books. The wrong way kick is not a leak in the accounting. It is a real feature of quantum mechanics, the same feature that lets waves cancel and reinforce, showing up in a place we never thought to look, in the gravity of a superposed mass. It is strange. It is not a way to cheat. There is a name for this kind of quantum result, for effects that appear when you prepare a system one way, measure it another way, and keep only the matching runs. Physicists call the strange numbers that come out of such measurements weak values, an idea worked out in the 1980s, and one of their peculiar properties is that they can land outside the range you would normally think possible. A measurement that, averaged over everything, gives a gentle pull, can, in a selected slice, read as a push. This sounds like sleight of hand until you realize it has been tested in the laboratory and other contexts, and it genuinely works. It is a real, if subtle, corner of quantum theory, not a loophole someone invented for this one paper. The three physicists did not bend the rules to get their result. They applied rules that were already there, already tested, to a situation nobody had thought to apply them to, and out came the wrong way kick. If weak values still feel like a cheat, here is a homely picture that captures the shape of it without pretending to be the full mathematics. Imagine you record the daily temperature in a city for a whole year, and on average it comes out mild, a perfectly ordinary yearly average. But now suppose you go back and keep only the days that happen to fall right before a snowstorm, and you look at just those. That selected slice will read far colder than the mild average, colder even than you might have thought the ordinary range allowed, because you deliberately chose the days that lean one way. You did not change the weather. You did not break the thermometer. The full year still averages out mild. But by selecting a particular subset defined by how things turned out, you pulled a reading out of the data that looks impossible next to the average. The wrong way kick is like that. Keep every run and gravity averages out attractive, mild, ordinary. Keep only the runs that end a chosen way, and in that slice the probe reads as pushed. Nobody fooled the universe. They just asked a very particular question of a very particular slice. And the honest answer to that particular question was a push. I want to draw the honest line very clearly now, because this is exactly where a careful person separates from a hype merchant. The push that comes out of this is not anti-gravity in any sense you have ever dreamed of. It is astonishingly tiny. It is astonishingly fragile. It appears only in selected runs of an experiment so delicate it has never been performed. It is an effective force, not a new fundamental one, which is a phrase worth unpacking. There is no new particle here, no new field, no gravitational charge you could switch on, no repulsive substance. There is only ordinary attractive gravity, the same gravity Einstein described, made to interfere with itself through the quantum superposition of its source. The repulsion is an appearance, a consequence of interference, not a new law of nature. Nothing about it lets you levitate a coffee cup. Nothing about it lets you build a floating platform, or a car that hovers, or a boot that lifts you off the ground. The gap between what this paper actually shows and what the word anti-gravity conjures in your imagination is enormous, and the whole credibility of the story depends on keeping that gap in full view. And yet, and this is the strange balance the video keeps returning to, none of that honesty makes the result small. Yes, it is tiny. Yes, it is an appearance rather than a new force. Yes, it would not lift a feather, but it would answer a question 100 years old. It would tell us that gravity is quantum. The value of the wrong way kick was never in its strength. A push you could feel would tell us nothing new. Forces you can feel are everywhere. The value is in its impossibility for a classical field. It is a small, fragile, selected, effective push that no smooth, definite gravity could ever produce. And that is worth infinitely more than a strong push that any ordinary force could fake. The size of the effect and the size of its meaning have almost nothing to do with each other. This is one of those places in physics where the smallest, most delicate thing carries the largest possible weight. It is worth sitting with that phrase, an effective force, for one more moment, because it is the honest heart of the whole result, and it is the thing most likely to get lost when a story like this travels. When physicists say a force is effective rather than fundamental, they mean it is not a new basic ingredient of the world, but a pattern that emerges from ingredients you already have. The push you feel from a crowd carrying you along in a stadium is real. You genuinely move. But there is no new force of crowd pushing in the laws of physics. It is ordinary pushes from ordinary people, adding up into something that looks like a single current. The wrong-way kick is like that. It is ordinary attractive gravity, the only gravity there is, arranged and interfered so that its net appearance in a selected slice is a push. That is not a lesser thing, and it is not a fake thing. But it is a precise thing, and the precision matters, because it is exactly what tells you the result is trustworthy rather than magical. A paper that claimed a brand new repulsive force of nature would deserve enormous suspicion. A paper that shows ordinary gravity can be made to look repulsive through quantum interference, and that this appearance could only happen if gravity is quantum, is doing something much more careful and much more believable. There is something almost reassuring buried in all of this, if you let yourself feel it. The universe did not hand these physicists a free lunch. It did not let them break a conservation law or build an impossible machine. It offered them something far more careful and far more interesting, a genuine strangeness that stays perfectly within the rules, a push that hides inside the pull without ever overturning it, a loophole that gives you a profound answer while refusing to give you a free ride. The floor does not give way. The books still balance, and yet tucked inside the most familiar force in your life, there is a real quantum surprise, waiting, honest, and almost impossibly hard to reach. Which brings us to a very human question, one that has nothing to do with equations and everything to do with why a title like this one stops you in the first place. If gravity has a door in it, even a tiny, fragile statistical door, then people were always going to want to walk through it. People have wanted to defeat gravity for as long as they have fallen down, and the history of that wanting, the long, strange, sometimes heartbreaking history of the human hunt for anti-gravity, is a story worth telling before we come back and ask how far this real result actually is from the dream. Because the dream came first and it came hard, and understanding it is the only way to see clearly what these three physicists did and did not do. Part 8. The Long Dream of Falling Up. The wish to defeat gravity is older than any equation, and it has a history that is by turns funny, sad, and strangely human, and I want to tell it honestly, because it is the shadow this real result is standing in front of. People have always wanted to fall up, and in the 20th century, that wanting occasionally hardened into serious, funded, sometimes desperate attempts to make it real. It begins, oddly enough, with grief. In 1948, an American businessman named Roger Babson founded an organization called the Gravity Research Foundation, and his motivation was not curiosity but loss. As a young man, Babson had watched a sister drown, and later a grandson, and in his mind he came to blame gravity itself, the force that pulled them down under the water and would not let them rise. He hated gravity the way a person hates an enemy, and he poured his considerable fortune into the dream of defeating it, of finding some material or method that could shield against it, block it, hold it off. The foundation he built to chase that dream sponsored an essay contest, and here the story takes its first strange turn, because that contest, born from one man's grief and his fantasy of a gravity shield, ended up attracting genuinely brilliant physicists, and over the decades several future Nobel Prize winners wrote for it. The dream was impossible, but the money and the attention it brought were real, and some real science grew in that odd soil. The wish was a fantasy. The yearning behind it was human enough to move serious minds. Then there are the inventors who claimed they had actually done it, and their stories are where honesty has to do its firmest work. In the middle of the 20th century, an inventor named Thomas Townsend Brown promoted something he called electrogravitics. He had noticed that certain high-voltage devices, capacitors charged to enormous voltages, seemed to produce a thrust, a push, when powered up, and he became convinced he had found a link between electricity and gravity, a way to generate an anti-gravity force with charge alone. For a while the idea attracted real interest, but when it was carefully investigated, the truth turned out to be far more ordinary. The thrust was real, but it had nothing to do with gravity. It was ion wind, charged particles in the air being flung off the device and pushing back on it. The same principle that makes certain silent electric fans work. Take away the air, put the device in a vacuum, and the mysterious anti-gravity thrust simply disappears, because there is no air to throw. The push was real, the anti-gravity was not. And then, in the 1990s, came perhaps the most tantalizing claim of all. A researcher named Evgeny Podkletnov, working with superconductors, reported something astonishing. He claimed that a superconducting disk, spun at high speed and kept extremely cold, could partially shield the space above it from gravity, so that objects placed over the spinning disk would lose a tiny fraction of their weight. If it were true, it would have been one of the greatest discoveries in the history of physics, the gravity shield that Babson had dreamed of. Laboratories around the world took it seriously enough to try to reproduce it, and no one, anywhere, ever could. The effect refused to appear in any careful independent test. It joined the long list of results that shine brightly for a moment, and then dissolve when the rest of the world reaches for them. Let me put you in that 1990s laboratory for a moment, because the human weight of it is worth feeling, and it is the counterweight to all the cold, clean rigour of the real paper we have been discussing. Picture a dim room, humming with equipment. Cold fog rolls off a cryostat, spilling over the edges of the table and pooling on the floor, because something inside is being held near the temperature of deep space. In the centre, a disk spins, faster and faster, a blur of motion kept impossibly cold. Above it hangs a small object on a delicate balance, and everyone in the room is staring at the needle of that balance, waiting. And the needle flickers. It dips, just slightly, as though the object above the spinning disk has become for an instant a hair lighter. The people in the room feel their hearts move. This is it. This is the thing humanity has wanted since the first person fell and could not rise. The dream, real, on a table, in front of their eyes. And then, in laboratory after laboratory, in country after country, other careful people build the same apparatus, spin the same kind of disc, hang the same kind of weight, and stare at their own needles, and the needles do not move. The flicker will not come again. And slowly, painfully, the dream deflates, not with a dramatic disproof, but with the quiet, grinding accumulation of nothing happening, over and over everywhere else. The needle that dipped becomes a thing that could not be found twice, which in science is the same as a thing that was never there. There is a pattern in all of this that is worth naming, because it is one of the quiet engines of real science, and it separates the dreams from the discoveries. A genuine result can be found twice. It can be found by strangers, in another country, who do not want it to be true, and it shows up anyway, because it is really there in the world and the world does not care who is looking. A false result, however sincere, however much everyone wants it, cannot survive that test. It appears once, in one lab, under one set of hopeful hands, and then refuses to come when anyone else calls it. The gravity shield, the electric anti-gravity thrust, the lightened weight over the spinning disk, all of them followed this second path. They flickered once and could not be summoned again. That is not cruelty on the part of the universe, it is honesty. Replication is how nature tells the difference between what we wish were true and what is, and it is precisely the test the new paper has not yet faced because the experiment it describes has never been performed. The idea is beautiful and the mathematics is sound, but the wrong way kick has not yet been found even once, let alone twice, and that distance is something we will have to look at squarely before the night is over. I do not tell these stories to laugh at the people in them. There is nothing to laugh at. The wish to lift the weight, to defeat the thing that pulls us all down in the end, is one of the most human wishes there is, and the people who chased it were not fools so much as dreamers who wanted badly for the universe to be kinder than it is. But their stories matter tonight for a specific reason, because they show, by contrast, exactly what the new paper is and is not. Every one of those old dreams was a claim to have beaten gravity, to have found a device or a material that overturns the rule. Every one of them promised the floating platform, the shielded weight, the car that hovers, and every one of them, when the world reached for it, was either ordinary physics in disguise or nothing at all. The paper by the three physicists is the opposite kind of thing in almost every way. It does not claim to beat gravity. It does not overturn Einstein. It does not promise a device or a material or a shield. It uses accepted, tested, ordinary quantum physics, applied with great care, to probe what gravity actually is, and the push it produces is not a triumph over the rule but a fingerprint of the rule's hidden nature. The dreamers wanted to defeat gravity. These physicists want to understand it, and that difference is everything. One is a wish thrown against the wall of reality, the other is a careful question asked of reality in its own language. The wrong way kick is not the gravity shield Babson prayed for. It is something smaller, stranger, and far more honest, and precisely because it is honest, it might, unlike all those bright dead dreams, actually be real. There is one more thing to clear away before we go on. A modern cousin of these old dreams. Some corners of the internet insist that working anti-gravity already exists hidden away, that governments or secret laboratories possess craft that defeat gravity and are keeping it from the world. It is worth saying plainly that there is no credible evidence for this, and that the actual physicists working on gravity are doing the opposite of hiding. They are posting their ideas openly on public archives for anyone in the world to read and check, which is exactly how this very paper reached us. Real science on gravity is not locked in a vault. It is out in the light, fragile and unfinished and honest, and that openness is a feature, not a cover story. The dream of falling up is old and powerful. The truth of it, when it finally arrives, will not come from a hidden vault. It will come, if it comes at all, from a cold, quiet bench where someone finally coaxes a speck of matter into two places at once. Part 9. Where the universe already pushes. There is a fair objection you might be forming by now, and it deserves a real answer, because it sharpens exactly what is new here. Does the universe not already contain repulsion? Have we not been told for years that the cosmos is being pushed apart, that space itself is flying outward faster and faster? If gravity can already push on the grandest scale, why is a tiny wrong-way kick on a laboratory bench such a shock? The answer is that the universe does contain repulsion, in a few specific and genuinely strange ways, and looking at each of them shows precisely why this new push is different from all of them. Start with the biggest one, the discovery that reshaped cosmology at the end of the 20th century. In 1998, two teams of astronomers, measuring the light of distant exploding stars, found something nobody expected. The expansion of the universe is not slowing down under the pull of all its gravity, the way everyone assumed it must be. It is speeding up. Something is driving the galaxies apart faster and faster, overpowering the inward pull of all the matter in the cosmos. We do not know what that something is, so we gave it a name that mostly marks our ignorance: dark energy. And dark energy behaves like a kind of repulsion built into the fabric of space itself, a pressure that pushes outward everywhere, growing more dominant as the universe grows larger and emptier. So yes, on the larger scale there is a push, and it is winning, and it will eventually carry every distant galaxy beyond our sight. There is another cosmic push in the story of the universe's birth. Most cosmologists believe that in the first unimaginably small fraction of a second after the beginning, the universe went through a burst of hyper-expansion called inflation, doubling in size again and again with astonishing speed, driven by a kind of repulsive gravity in the conditions of that first instant. And going further back into theory, physicists since at least the 1950s, including Hermann Bondi in 1957, have played with the mathematics of negative mass, a hypothetical kind of matter that would gravitationally repel rather than attract. On paper, negative mass would push. It would make the rubber sheet rise into a hill instead of sagging into a valley. But here is the crucial fact. No negative mass has ever been found, anywhere, in any experiment. It remains a mathematical possibility with no known example in the real universe. So the universe does push, in these ways. Why is the wrong-way kick still a shock? Because every one of these cosmic repulsions is a completely different kind of thing from what the paper describes, and the difference is the whole point. Dark energy and inflation are properties of space, and the vacuum on the larger scales, a feature of the emptiness itself, not a repulsion between two ordinary lumps of matter. Negative mass is hypothetical, never observed. What the three physicists claim is far more surprising in one exact way. They are describing a push between ordinary positive masses, the same kind of matter you are made of, the same kind that has only ever attracted, arising purely because one of those masses has been placed into a quantum superposition. That has never been seen and was never thought possible. The cosmos pushes with the vacuum and with the hypothetical. The paper pushes with a speck of ordinary matter made quantum. Those are not the same discovery wearing different clothes. They are entirely different animals. It is worth pausing on just how strange dark energy is, because it is the closest thing the real universe has to a genuine working anti-gravity, and even it is nothing like the push in the paper. Dark energy does not pull galaxies apart by acting on them from outside. It is woven into empty space itself, so that every cubic meter of vacuum carries a faint outward pressure, and because a larger universe has more vacuum in it, the push grows as the cosmos expands, feeding on its own success. It is the reason the far future of the universe is a lonely one. Given enough time, this repulsion will carry every galaxy outside our own, beyond the horizon of what we can see, until the sky empties. That is a real, cosmic, relentless push. And yet it tells us nothing about whether gravity is quantum, because it is a property of space, not an interaction between two masses. You could know everything about dark energy and still not know the answer to the 100-year question. The wrong-way kick, tiny as it is, would answer that question in a single run. That is the difference between a huge push that is silent about the nature of gravity and a microscopic one that speaks volumes. And there is a beautiful, humbling counterpoint from the real world, a recent experiment that shows just how stubborn gravity's one-way rule really is. For a long time, one of the most intuitive candidates for antigravity was antimatter. Antimatter is the mirror image of ordinary matter, identical but with opposite electric charge, and it is real. We make tiny amounts of it in laboratories. For decades, a tantalizing question hung in the air. Does antimatter fall down, like ordinary matter, or does it fall up? Might antimatter be the negative mass stuff, the thing that gravity repels? It was a genuine open question, and answering it required heroic effort, because antimatter is so hard to make and hold. Finally, in the year 2023, an experiment at the European laboratory CERN managed to do it. They made atoms of antihydrogen, held them, released them, and watched which way they fell. And they fell down, just like ordinary matter. Gravity pulled the antimatter exactly the way it pulls everything else. Even the most intuitive candidate for a gravitational push obeys the one-way rule. It is hard to overstate how much effort went into that plain little answer. Antimatter and ordinary matter annihilate the instant they touch, vanishing in a flash of energy, so to weigh antihydrogen you first have to make it, atom by painstaking atom, then hold it suspended in magnetic fields so it never brushes the walls of its container, then cool it almost to a standstill, and only then let it go and watch, with instruments of extraordinary delicacy, which way it drifts as it falls. Years of work for a one-word answer, and the answer was down. Not up, not sideways, not a hair lighter, down at the same rate as everything else, within the precision they could measure. The mirror matter that a century of imagination had cast as the most likely rebel against gravity turned out to be gravity's most obedient subject. Every romantic loophole the universe seemed to offer for a push between ordinary bodies has, one by one, been closed. Which leaves the quantum loophole standing alone, the only door not yet slammed shut. I find something quietly moving in that result. We reached out to the one form of matter that seemed like it might rebel against gravity, the mirror stuff, the antimatter, and we asked it plainly, which way do you fall? And it fell down like a stone, like an apple, like everything that has ever been let go. Gravity's refusal to push is so complete that the universe only seems to bend the rule at the two extreme ends of scale, out at the largest reaches, where dark energy drives the emptiness apart, and down in the smallest, most delicate quantum arrangements, on paper, in the fine print of a superposition. And in between, on the human scale, the scale of dropped cups and held hands and antimatter falling like rain, gravity has never once, in all of history, been caught pushing. That is where you live, on that middle scale. You live on the one stretch of the ladder where gravity has only ever pulled. The exceptions are far above you, in the expansion of the cosmos you will never feel, and far below you, in the quantum arrangements you will never touch with your bare hands. The force that holds you in your chair belongs to the wide, unbroken middle of the ladder, the part where the rule has never once bent, which is exactly why the wrong-way kick, if we could ever drag it up out of the quantum fine print and onto a real bench, would be such an astonishment. It would be a piece of the impossible ends of the ladder, brought into the middle, into a laboratory, into a place where a person could, in principle, watch it happen. It would be gravity behaving in a human-sized room, the way it is only ever supposed to behave in the birth of the cosmos, or the fine print of a quantum equation. No wonder the word terrifying attached itself to the idea. Something that belongs only to the extreme edges of reality would, for one flickering run, be sitting on a bench in front of you, in an ordinary room, under ordinary light. But that word, could, is doing an enormous amount of work in that sentence, and it is time we looked at exactly how much. And that brings us to the hardest and most honest part of the whole story, the part the dreamers never wanted to hear. Just how far is that bench from anything we can actually build? Part 10. 20 micrograms and 2 million times. Now comes the honest cold water, and I'm not going to soften it, because respecting this part is what separates understanding the paper from being fooled by a headline. The experiment the three physicists describe, the one that would produce and detect the wrong way kick, is, with today's technology, impossible. Not difficult, not expensive, impossible by a margin so large it is hard to hold in your mind. Let me give you the number that makes it real. To run this experiment with a realistic probe, and the authors work through the case where the probe is made of cesium atoms, the source mass, the object you have to place into a clean quantum superposition of two positions, would need to weigh about 20 micrograms. 20 micrograms sounds like nothing, and in one sense it is nothing. It is a speck. It is a fraction of the weight of a single grain of sand, far too small to see clearly, far too light to feel in your hand. And that is exactly what makes the situation so humbling. Because to take that invisible speck and place it into a genuine quantum superposition, in two positions at once, and hold it there long enough to measure its gravity, is roughly 2 million times beyond anything any laboratory on Earth can currently do. Remember the ladder of superpositions we climbed earlier, the buckyball of 60 carbon atoms, the molecules of more than 2,000 atoms. Those were triumphs, the largest things we have ever coaxed into being in two places at once, and they are millions of times lighter than this speck. The gap between what we can superpose today and what this experiment needs is not a step. It is not a staircase. It is a canyon, and right now we're standing on one rim of it, looking across at a far wall we have no bridge to reach. It helps to try to feel the size of 2 million times, because numbers like that go numb the moment you hear them. If you had a single dollar and I told you that you needed $2 million, you could at least picture the pile. But this is not a gap in quantity so much as a gap in what is even possible with our best techniques. It is closer to the difference between the highest a person has ever jumped and the distance to the moon, except that in the jumping case we at least know how rockets work. Here we do not yet know the equivalent of the rocket. We know how to superpose things up to a certain weight, and past that weight the methods we have simply stopped working, and the object crashes out of its superposition before you can do anything with it. Getting from the heaviest superposition ever achieved to the weight this experiment needs is not a matter of building a bigger version of the same machine. It would take new physics of control, new ways of holding the quantum world open that nobody has yet invented. That is what 2 million times means here. It means a discovery, or a whole series of them, standing between us and the bench. This is where the dragon of decoherence comes back, larger than ever. The heavier the object, the faster its quantum blur collapses, and 20 micrograms is astronomically heavier than anything we have held in superposition. To keep something that heavy in two places at once, even for an instant, you would have to defeat decoherence to a degree that current physics has no idea how to achieve. The authors are honest about this. They do not hide it. And they point, carefully, to the things that could, in principle, narrow the canyon over time. If we learned to keep superpositions alive longer, holding off decoherence, the required mass would drop. If we learned to measure forces far more precisely, so that a fainter effect could still be detected, the required mass would drop. If we learned to work at shorter distances, where gravity between the source and probe is stronger, the required mass would drop. Advances on any of these fronts would shrink the gap. But even in the most hopeful accounting, this is a proposal for some future generation of physics, not for this decade, and quite possibly not for this century. And it gets more sobering still, because even if some future laboratory did manage to build the impossible apparatus and did see a wrong-way kick, the trouble would not be over. This is the point the careful skeptic pressed hardest, and it is a fair and important one. Gravity is the weakest force by an enormous margin, which means that at the tiny scales of this experiment, all sorts of other, much stronger forces are lurking, ready to produce a push that could look exactly like the one you're hunting for. A stray whisper of electric charge, a faint magnetic field, a subtle effect of the quantum vacuum between two close surfaces. Any of these could nudge the probe the wrong way and masquerade as a gravitational push. So even a positive result, even an actual observed kick, would face a brutal challenge, proving that it was gravity that did it, and not some ordinary force wearing gravity's costume. That is why one well-known physicist reviewing this paper gave it a low score as a practical experiment, something like a 2 out of 10, even while praising it warmly as a genuine and clever contribution to the ideas. The math is beautiful. The path to actually seeing it is a minefield. There is one more twist of the knife, and it is the kind of thing that makes this field so maddening and so honest at once. Suppose the experiment were run and no kick was ever seen. You might think that would at least settle the question the other way, prove that gravity is not quantum. It would not. A negative result would prove almost nothing, because it might simply mean that this particular quantum signature did not show up under these particular conditions, not that gravity lacks quantum properties altogether, so the experiment is asymmetric in the cruelest way. A positive result would be revolutionary but nearly impossible to trust. A negative result would be inconclusive, a silence that could mean anything. That is the honest shape of the thing, and any account that leaves it out is selling you something. It is worth admiring the paper precisely for surviving this scrutiny, with its dignity intact. It never promised the experiment was easy. It offered a clean idea, a genuine new way to think about catching gravity in a quantum act, and it laid out its own difficulties plainly, which is exactly what honest science looks like when it is working. I want to slow all the way down now, because underneath all this careful hedging is a feeling I think is the real centre of the whole video, and it has been waiting patiently for us this entire time. Here is the strangest fact of the night, and it is not about pushes or superpositions or micrograms. Gravity is the force you know best. You have felt it every single second of your life, without one moment's pause, since before you were born, when it pulled gently on you in the dark. It is the most constant companion you will ever have. It will be there in your last moment as surely as it was in your first. You understand it in your body more completely than you understand anything else. You have a lifetime of the most intimate possible acquaintance with it, and it is the force physics understands least. We can predict its pull to a precision that lets us land machines on other worlds, and we still cannot tell you what it is, or whether it obeys the same quantum rules as everything else in the universe. The thing that is closest to you, touching you right now, holding you in this chair, is the greatest stranger in all of physics. We have never even settled the most basic question about its nature. The most familiar force in your life is the one we have never truly met. There is a particular kind of humility in that, the humility of the expert who knows exactly where the map runs out. It would be easy to assume that a force we can predict so precisely must be a force we understand. But prediction and understanding are not the same thing, and gravity is the clearest proof of the gap between them. We can say, with astonishing accuracy, what gravity will do. We cannot yet say what it is, or whether at its foundation it is woven from the same quantum thread as light and matter and everything else. For 3 centuries we have been like someone who knows a person's habits perfectly, who can predict their every move, and who has never once seen their face. The wrong way kick, if it could ever be seen, would be the first look at that face. Sit with that for a moment, in the quiet. Not as a fear, but as a kind of wonder. You are being held gently and constantly by something no one on Earth fully understands. Every scientist who has ever lived, every equation ever written, and still, when a child asks what gravity really is, and whether it plays by the same rules as light and matter, the honest answer is a shrug and a promise to keep looking. That is not a frightening thought once you let it settle. It is an astonishing one. It means that the most ordinary experience you have, the simple fact of your own weight, sits on top of one of the largest unanswered questions in all of science. And it means that a cold, quiet bench, with a speck of matter in 2 places and a probe drifting the wrong way, is not really an experiment about anti-gravity at all. It is an experiment about finally meeting the stranger who has been holding us our whole lives. So let us imagine, gently and honestly, what it would mean if that meeting ever actually happened. Part 11. If the kick is real. Let us allow ourselves for a little while to be generous. Suppose that some future generation, armed with tools we cannot yet imagine, builds the impossible apparatus. Suppose they hold a speck of matter in 2 places at once, and they watch a probe, and they see it drift the wrong way, and they do the patient, brutal work of ruling out every stray force, every whisper of charge, every quantum vacuum effect until they are certain, truly certain, that what pushed that probe was gravity. What would that actually change? Not, to be clear, your commute. This gives no one a floating car. We have buried that dream honestly, and it stays buried. What it would change is something far larger, in a completely different direction, and to see it you have to follow the thread all the way down to the beginning of everything. The first thing it would change is the 100-year stalemate itself. It would be the first direct evidence that gravity is quantum, the crack of light under a door physicists have been pressing against since before your grandparents were born. Every other force in nature has been brought into the quantum fold. Gravity alone has stood outside, and we have never been able to say for certain whether it belongs there. A confirmed wrong-way kick would settle it. It would tell us that the gravitational field, like every other field, can exist in a superposition, can be in more than one state at once. And that single fact is the missing clue that every attempt to build a real theory of quantum gravity has been waiting for. Remember the two instruction manuals, the one that says assemble with screws and the one that says there are no screws. The wrong-way kick would be the first sentence that could be written in both manuals at once, the first place the two maps overlap instead of contradict. It would not finish the theory, but it would tell the theorists at last which direction to walk, and after 100 years of not knowing, that would be everything. It is worth dwelling on how much rides on that one-directional clue, because from the outside it can seem like a small technical prize. It is not. A working theory of quantum gravity would be the closest thing physics has ever had to a single description of everything, one set of rules underneath both the large and the small, the manual that finally has all the right pages. It would let us describe the places where our current theories go blind, the centers of black holes, and the first instant of the universe, without the mathematics collapsing into nonsense. It might tell us where space and time themselves come from, whether they are truly fundamental, or whether, like temperature, they are large-scale appearances that emerge from something more basic underneath. Physicists have been circling these questions for a century, able to ask them but never to answer them, precisely because they have never had one confirmed fact about how gravity behaves in the quantum world. The wrong-way kick would be that fact. One clean observation, and 100 years of pure speculation would suddenly have a piece of solid ground to stand on. That is why people who understand the stakes get quietly emotional about a result that, on its surface, is just a particle nudged the wrong way on a bench. And here is where the thread reaches all the way down to the beginning. In Einstein's classical gravity, if you follow the equations backward or inward, they lead you to places where they break, points of infinite density that physicists call singularities. There is one at the center of every black hole, where matter is crushed down past all limit, and there is one at the very start of the universe, the Big Bang itself, where everything that exists now was packed into something smaller than a point, and the mathematics simply stops making sense. These singularities are not features anyone believes in literally. They are the theory raising its hands and admitting it has reached the edge of what it can describe. Almost every physicist believes the singularities are not real, that they are signposts saying, here you need a better theory, here you need quantum gravity. And a quantum theory of gravity, one in which gravity can in some sense push at the smallest distances, offers a way to erase them. Think about what a short-range gravitational push could do at the moment of ultimate collapse. In the classical story, matter falling into a black hole, or the whole universe running backward toward its start, just keeps collapsing forever, down to an impossible point. But if gravity, at close enough range and high enough density, can turn from a pull into a push, then the collapse would not reach the impossible point. It would reach a floor, the infalling matter would be halted, held, and driven back out. And applied to the birth of the universe, this gives one of the most beautiful ideas in modern cosmology a real physical footing. Perhaps the universe did not begin at a singularity at all. Perhaps what we call the Big Bang was not a beginning from nothing, but a bounce, a rebound, the moment a previous contraction hit the quantum floor and turned around. A big bounce instead of a big bang. Let me take you to that moment gently, and let it be one possibility among several rather than a certainty, because that is exactly what it is. Imagine the instant that classical physics cannot describe, the instant everyone was taught to think of as the beginning. In the old picture, you run time backward and everything rushes together, smaller and hotter and denser, until it all piles into a single point of infinite density, and the story just stops, with no before, no explanation, only an edge. But now imagine it differently. Imagine that as everything rushes together, as the density climbs past all reason, gravity itself begins to change its nature. The pull that has been drawing everything inward, at the very last moment, at the smallest scale, becomes a push, and instead of crushing down to an impossible point, the whole contracting cosmos reaches a floor it cannot pass, a density beyond which gravity will not let it go, and it stops, and it turns, and it begins to expand. What we have always called the first instant becomes a hinge, a turning point, a single breath, the universe breathing in before it breathes out. There was a before. There was a previous cosmos contracting that reached the floor and rebounded into ours. The beginning was not a wall, it was a bottom, and something bounced off it. The same reprieve would reach into the hearts of black holes. In the classical picture, anything that falls into a black hole is drawn inexorably down to that central point of infinite density, a place where everything we know about physics simply gives out. It is one of the most unsettling ideas in all of science, this notion of a genuine edge inside reality, a point where the story ends. But if gravity can push at the smallest scales, then the matter falling inward would not have to crush down to an impossible point. It could reach a floor, a finite quantum core, dense beyond imagining but not infinite, not a place where physics dies. The black hole would hide not a singularity but a heart, strange and small and finite. And some physicists have followed that thought to a wondrous conclusion, that a collapsing core reaching its floor and rebounding might in some sense be a bounce of its own, so that the death of a star and the birth of a cosmos could be, at the very bottom, the same kind of event. All of this hangs on the same thread. Whether gravity, at the smallest scales, can do the one thing the wrong way kick would prove it can, whether it can push. I have to hold that image loosely, and I want you to as well, because it is speculation resting on speculation. We have not seen the wrong way kick. We do not have a finished theory of quantum gravity. The Big Bounce is one idea among several serious attempts to describe what a quantum beginning might look like, and it is not established science. But it shows you why a tiny, fragile 2 million times out of reach push on a laboratory bench is not a small thing at all. Because that same quantum nature of gravity, the thing the wrong way kick would witness, is exactly what physicists need to erase the singularities, to give black holes a finite heart instead of an impossible point, and to turn the beginning of everything from a wall we cannot see behind into a floor that something rebounded from. Some physicists have even wondered, far out on the speculative edge, whether a quantum gravity that sometimes pushes might reduce the need for a separate dark energy to explain why the cosmos is flying apart. These are ideas, not conclusions, but they are the reason this thread matters. Pull on a wrong way kick on a cold bench, and the thread runs, unbroken, all the way to the first instant of time and the darkest hearts of the sky. That is the size of what is hidden inside this small, strange result. Not a floating car, not free energy. But a possible answer to the oldest question there is, the question of what holds everything together and what happened at the very start tangled up with a speck of matter placed into two places at once. Which means the fear the title promised, the terror, was never really about anti-gravity at all. It was about something much closer to home and much harder to shake. It was never the fear of floating or of falling or of some machine gone wrong. It was a quieter thing, waiting under all the equations, and it is time, at last, to name it honestly and to turn it, gently, into something you can carry with you into sleep. Part 12. The terror was never floating. So let us name the fear plainly, now that we have earned the right to. When you saw that scientists had proved something terrifying about anti-gravity, some part of you may have braced for a threat, a danger, a machine that could switch off your weight and send the world tumbling. That was never it. What the three physicists proved on paper is not that we can defeat gravity. It is that the most familiar force in your entire life, the one you have trusted since before you could speak, the one holding you right now, has a hidden door in it that we never knew was there, and that behind that door is a question we cannot yet answer about what gravity truly is. That is the terror. Not that gravity might push, that we have been held gently and constantly our whole lives by something we do not understand. And I want to spend these last minutes turning that fear over in your hands, slowly, until you can see its other face, because it has one, and its other face is not fear at all. Go back to the very first thing we said tonight, the one rule that never breaks. Whatever you hold, if you open your hand, falls. The force that only ever pulls. We built the whole night on that certainty, and it is still true, in every ordinary moment you will ever live. Your cup will still fall tomorrow, the moon will still hold its orbit, nothing about your daily life has changed, but you know something now that you did not know when we began. you know that the rule that only ever pulls was never quite the whole story. That hidden inside it, written into the mathematics all along, waiting 300 years since Newton and 100 since Einstein, was the possibility of a push. The rule you were most certain of had a door in it the entire time, and that is not a frightening fact once you turn it toward the light. It is a hopeful one. Because if the most exceptionless rule in your experience can still surprise you, still hold a hidden door, then the universe is not a closed and finished thing. It is not a room whose walls you have already mapped. It is still, after everything, full of doors you have not found. Remember the two instruction manuals, the two flawless contradictory descriptions of reality that a century of the finest minds could not make agree. It would be easy to hear that as a failure, a sign of how little we know. I would ask you to hear it the other way. The seam between those two manuals, the crack where general relativity and quantum mechanics refuse to meet, is not a wound. It is the most exciting frontier in all of science, the one place we are most certain something enormous is still waiting to be found. And the wrong way kick is a lantern held up to that seam, a way, however faint and far off, of reading a single sentence in both manuals at once. We are not living at the end of physics, with everything discovered and only the details left. We are living in the middle of the greatest unsolved mystery there is, and we have just found a new way to ask the universe about it. That is not a reason for dread. That is a reason to be quietly, deeply glad you're here to see it. And remember the wrong way kick itself, that small, strange push, gravity for one flickering instant running backward. I told you early on that the push was not the point, that it was a witness, a flag, a signal. But there is one more thing it is, and it is the thought I want to leave you holding as you drift off. Every real revolution in the history of physics was a wrong-way kick. Everyone. Someone did a careful experiment and the needle moved the wrong way, opposite to where the textbook pointed, and for a moment it looked like a mistake, or a broken instrument, or a violation of something sacred. The planet Mercury drifted the wrong way, and it gave us Einstein. Light behaved the wrong way, and it gave us quantum mechanics. Over and over, the universe has moved opposite to where our certainty pointed, and every single time that wrong-way motion was not a catastrophe. It was a door. It was the universe telling us gently that our map was not yet finished, and inviting us to draw a little more of it. The wrong-way kick in this paper, if it is ever seen, would be one more of those invitations, perhaps the largest one yet. And even if it is never seen, the pattern holds. The surprises are not threats. They are the shape of discovery itself. Now let me bring it all the way home, to you, lying there in the dark. You are made of the same matter as that speck on the cold bench, the same atoms that only ever attract, the same ordinary positive mass. And you are held together, this very moment, by the force we have spent the whole night failing to fully understand. Gravity is inside you and around you and under you, holding your blood in your veins, holding you to the bed, holding the whole planet beneath you together so that there is a bed to lie on at all. You're a small, warm, temporary knot of the very thing that physics cannot yet explain. And here is the wonder that I think outshines every fear in this story. That knot of unexplained force, that small arrangement of attracting matter, somehow woke up. It became something that can look at the force holding it down and wonder what that force is. You are gravity and matter and quantum strangeness, folded together into a shape that can ask questions about itself. In all the reaches of the sky, in all the pulling and the falling and the immense silent turning of the galaxies, that is the rarest and strangest thing we have ever found. Not the push, you, the part of the universe that looks up and wonders. There is a symmetry in that which I find almost unbearably lovely, and it is worth saying slowly. The same force that has never once let you go, that held you before you had a name and will hold you at the very end, is also the one force we have never been able to fully explain. The thing that grips you most tightly is the thing that slips most completely through our understanding, and you, held by it, made partly of it, are the only kind of thing we know of anywhere that can turn around and ask what it is. The galaxies are held by gravity and do not wonder about it. The stars are held by gravity and do not ask. Only here, in these small warm knots of matter that call themselves people, has the universe folded itself into a shape that can look at the force in its own body and say, what are you, and how do you work, and why do you only ever pull? The wrong way kick is the universe, through us, beginning to answer its own question. That is what a laboratory is in the end. It is the cosmos leaning close to a mirror, trying to make out its own face. And none of this asks you to hold the mathematics, or to remember a single number, or to follow the interference of two crests on a pond. It asks only that you let the ordinary become strange again for a moment, that you feel your own weight and remember it is a mystery, that you notice you are being carried and do not know entirely by what. Children feel this before they are taught not to. Somewhere along the way, most of us stopped noticing the miracle of simply being held to the ground. Tonight, for a little while, you noticed again. So the next time you feel your own weight, when you sink into your chair at the end of a long day, or lie down tonight and feel the bed take you, I hope you feel it a little differently now. That gentle, constant pull is the oldest and most faithful presence in your life, and it is also one of the greatest unsolved mysteries in all of science. And both of those things are true in the same quiet moment. You're being held by something no one on earth fully understands, and instead of frightening you, I hope by now, that steadies you. Because it means the universe still has secrets, still has doors, still has wrong-way kicks waiting to be found. And it means that you, a small knot of that same mysterious force, got to be here, for a little while, awake, wondering, held. What scientists proved about antigravity was never really about floating. It was about how little we know of the thing that holds us, and how much wonder is still hidden inside the most ordinary moment of your life. That is not terrifying. Once you have followed it all the way down, it is the most reassuring thing I know. The force that only ever pulls has a door in it. The two manuals may yet be read as one, and you are here, held gently against the turning earth, to hear about it. Let the day go, and let the questions stay open, because open questions are the most alive thing in the universe, and you are lucky beyond measure to be here among them. Rest now. Gravity has you. It always has, in every room, on every night since the very beginning. And for once that is not a fact to fear, but a mystery to fall asleep inside of.